Hello students, this is video 9K. I'm going to talk more about R squared, continuing where Joe left off. So more on R squared. Remember, R squared is the percentage of variation in your y variable that can be explained by your linear regression equation. So if you had an R squared value of 0%, that would mean that none of the variation in your y variable was captured by the linear equation. If that's the case, then your linear equation is virtually worthless. And we wouldn't feel comfortable using that equation for prediction, as the points would be randomly scattered with no linear pattern there at all. Okay, the other extreme with R squared. What if R squared was 100%? That would mean that all of the variation in the y variable was captured by the linear equation. The only way that that can happen is if all of your points fall exactly on that straight line. And so if that was the case, we'd feel very comfortable using our equation for prediction. All right, so we've kind of had the two extremes, 0%, 100%. What's a good R squared value? And we don't have a good answer for that question. It really depends on the context of the problem. So we're going to give you a couple of cases that are a bit extreme, but that show that there is no exact value there that's a good R squared value. Obviously, the larger your R squared value is, the more of the variation in y that's explained by your regression equation. So let's look at these couple of examples. So the first one major company developed a method to differentiate between two proteins. And to do that, they had to distinguish between regressions that had R squared values of 99.99% and 99.98%. And so for this particular application, to make that fine distinction there, an R squared value of 99.98% was not good enough. Typically in the problems that we look at, if we get an R squared like that, we'll be very excited and think that that's wonderful. But this is, just in context, for this particular problem, they had to make that fine of a distinction so that R squared value was not good enough for what they were doing there. Second example is sort of the other extreme. Separately, the president of a financial services company reports that although his regressions give only an R squared of 2% of the variation in his y variable could be explained by his regression, they are highly successful because those of his competitors are even lower. So just knowing that 2% that's explained gave him an edge over his competitors. Again, for most of the things that we look at, if we get an R squared value of only 2%, we're going to think that's pretty poor. But in this particular example, in the context of this problem, that gave him an edge. So we don't really have a definitive cutoff that these are some good R squared values. It does depend on the context of the problem, and we'll continue to practice interpreting those. Okay, so we've said this, but just to put this up here again, R squared, remember, measures the percentage of variation of the x variable that can be accounted for by the x variable that we've chosen to create the linear equation. So it measures the percentage of variation. We'll always talk about it as a percentage. And the percentage of variation in y that's accounted for by the chosen x variable that's used to create our linear equation. And so obviously the more variation that can be explained by your model, then the better that your equation is. All right, let's look at some examples. Oh, not yet. One more. One thing. Even though a higher R squared is better in general, you don't want to put all the weight on just the R squared value. You want to keep in mind the whole context of a problem. So a solid analysis of a linear relationship between two variables would include several things. You have to start with your scatter plot. If your scatter plot between your two variables is not linear, if it's curved or shows no relationship, then all this other stuff doesn't mean anything. So don't forget to start with your scatter plot. If your scatter plot looks good, then we would include a linear equation as part of our analysis, as well as R squared. You might throw in here that we also talked about residual plots. Residual plots are good for validating that the linear model is a good choice. So you might squeeze in here that a residual plot would be a good thing to look at as well. But just because you have a high R squared value, if R squared is 99.5%, but your scatter plot looks like it has a curve, your residual plot shows lots of outliers and no equal spread, then that high R squared value doesn't validate that you have a good model. When we do look at R squared, as long as everything in conjunction works out, we'll always write a sentence to interpret it. We won't simply say R squared was 99%. We'll always write a sentence to explain what that means. And when you do that, make sure that you do that in the context of the problem. What does it mean relative to what you're looking at? So that's what we're going to practice in the next couple of examples. All right, the first one. In your notes, you've got a few scatter plots here. So with this first one, this came from 58 stat students reported the model year of the car that they were driving, as well as the miles per gallon. We're trying to see if we can use the year of the car to help explain the gas mileage. So you can see what the scatter plot looks like here. The linear equation had an R squared value of 3.5%. So first off, when you look at the scatter plot, you don't right away say, oh wow, nice linear relationship between these two variables. This is more of like a random scattering of points. So a linear model might not have been the best choice for this one based on the scatter plot. But if you did run a linear model, you'd get an R squared value of 3.5%. That would tell you that 3.5% of the variation in those gas mileages could be explained by the linear model with year. Not very good. So a few things about this one. Linear model might not be the best choice. And really, I'm not so sure what the best choice is here. This, again, looks like no relationship to me. That 3.5% tells us that 3.5% of the variation in gas mileage per gallon can be explained by the year of the car. And so the year of the vehicle is not a very good predictor of gas mileage in this case. If 3.5% of the variation can be explained, 100 minus that, the other 96.5% could not be explained. It's due to other things. Really, we could probably come up with some other variables that might have a much stronger relationship with your gas mileage besides year. Perhaps how heavy your car is might be a better predictor. So this would be the interpretation. However, overall, probably not a good choice to fit a linear model to this set of data. All right, let's look at another one. B. A health food blog created a linear equation to predict calories based on fat grams. We looked at 50 fast food chicken sandwiches, and the analysis had an R squared value of 82.5%. Okay, this scatter plot looks much better than the previous one. If we use fat as our explanatory variable to predict calories, we see a nice, fairly strong here positive linear relationship between those two variables. The way we would interpret the R squared value of 82.5%, those 50 sandwiches, they didn't all have the same number of calories, right? So the number of calories varied. If we looked at all the calorie values for those 50 chicken sandwiches, 82.5% of the variation in those number of calories could be explained by the grams of fat in the sandwiches. So that's pretty good. And so we want to make sure that we write a sentence, sort of like what I just said, in the context of the problem to interpret that value. So for this one, 82.5% of the variation in calories can be explained by the grams of fat in the sandwich. So that seems pretty good. There is still the other 100 minus that, the other 17.5% is unexplained or due to other factors. And clearly there's other things that affect the amount of calories in a sandwich besides just the grams of fat, so that's where this unexplained percentage comes into play. Okay, last one. For this one, Professor Koop found 31 used Toyota Avalons. He created a linear equation to predict the price of those Toyotas based on the mileage. He got an R-squared value of 76.7%. So we're using mileage to help predict the price of the car. Not surprising that there's a negative relationship between the variables. But the issue with this one, the R-squared value is a decent value. But when you look at that scatter plot, don't forget, don't just look at R-squared all by itself. When you look at this scatter plot, would you describe this as linear? And really, I'm thinking that you should see a curve here. So the relationship here looks curved. If you have a curved relationship, you shouldn't interpret that R-squared value when you built a linear model. We should go back, do this again, and instead of choosing a linear model, we should pick something nonlinear for this one. So the big thing here is that this relationship is nonlinear. So we're not going to interpret R-squared. We would go back and create a different model, create a nonlinear model. I think we're going to hit on nonlinear equations probably in lesson 10. Okay, that's it for this lesson. Thanks.